This is the first lecture on X-ray production. Let's look at the objectives for today. After today's lecture, students should be able to describe Bremsstrahlung X-ray production and characteristic X-ray production. Students should be able to identify filtered versus unfiltered X-ray spectra, as well as the distinction between continuous and discrete spectra. Students should also understand how X-rays are influenced by the type of target materials used, the amount of filtration, as well as the electron energy or tube potential. I will start off with a brief historical overview. In the mid to later 19th century, scientists were studying electrical discharge in gases. The Crookes tube was a partially evacuated tube invented by William Crookes for this purpose. When a high voltage is placed between the electrodes, the air in the tube is ionized. The positive ions are accelerated to the cathode and the negative free electrons to the anode. The ions striking the cathode produce additional electrons that are accelerated to the anode to produce a glow on the screen or a shadow if an object like the Maltese cross is present. When the potential between the electrodes is high enough, say greater than 5 keV, the electrons are accelerated with enough energy to create X-rays when they strike a target. Röntgen discovered X-rays while using the Crookes tube in 1895. He named it X-rays because X stands for an unknown quantity. The Crookes tube is a cold cathode tube, meaning the cathode is not heated. In 1913, Coolidge improved the X-ray tube by introducing a heated wire filament. The Coolidge tube is a prototype of the modern X-ray tube in use today. It is more efficient at producing X-rays than the Crookes tube. The top left figure is of the Crookes tube. A modern X-ray tube is shown on the bottom left, and a picture of the Crookes tube is on the right. X-ray production has not changed much over the years. The process of Bremsstrahlung X-ray production is shown on this slide. An incident electron can either get very close to the nucleus or pass with very little interaction. If the interaction is weak, the electron suffers very little deflection, so the X-ray produced is very low in energy. This is shown by the number 3 electron. This type of weak interaction is the majority of interactions occurring. If the electron gets very close to the nucleus, it experiences a strong interaction and suffers a large deflection, leading to the production of a high energy X-ray. This is shown by the number 1 electron. This type of interaction is the least likely to occur. Because of the wide range of probable interactions, there is a spectrum of X-ray energies produced. This is a continuous spectrum called the Bremsstrahlung spectrum. Recall that when a charged particle like an electron interacts with atoms in matter, it deposits its energy by excitation and ionization as well as radiative energy losses. It is also possible that the electron will collide with the nucleus, leading to collisional energy losses in the form of heat. Most of the electrons produced in an X-ray tube deposit their energy in the form of heat due to collisions with the target. Only a small percentage, less than 1%, produce X-rays. For a given target material, the proportion of electrons producing X-rays increases with the electron energy or tube potential. We can say the Bremsstrahlung spectrum is the probability distribution of X-ray photons as a function of photon energy. There are two types of Bremsstrahlung spectra. There is an unfiltered spectrum and a filtered spectrum. This figure shows the unfiltered spectrum, which is the straight line, and the filtered spectrum, which is the curve. The unfiltered spectrum shows an inverse linear relationship between the number and energy of X-rays produced, with the highest energy determined by the peak voltage applied across the tube. In this figure, we shall focus on the filtered X-ray spectrum. The filtered X-ray spectrum has no X-rays below about 10 keV. Those X-rays are removed by the filter. The relative X-ray output increases to a maximum at about 1/3 to 1/2 of the maximal energy and then decreases to 0 at about the maximal X-ray energy. The peak location in the filtered spectrum is called the effective energy. For our purposes, the Bremsstrahlung spectrum is the most important for X-ray imaging. The spectrum depends on the electron energy in the X-ray tube. A higher electron energy means a higher maximal X-ray energy and also a higher effective energy for the filtered beam. I mentioned a few slides back that most of the electron's energy goes to heat production in the anode and that less than 1% produce X-rays. This is because X-ray production is inefficient. Major factors that affect X-ray production include the atomic number of the target Z, and the kinetic energy E of the electron in the X-ray tube. This formula is an approximate ratio that describes the relationships between Bremsstrahlung X-ray production, called radiative losses here, versus collisional energy losses. On the previous slides, we have been talking about Bremsstrahlung X-rays, which are a continuous spectrum of X-rays. In addition to this continuous spectrum, discrete X-ray energy peaks called characteristic X-rays can also be present. The location of these characteristic peaks depends on the elemental composition of the target material. It is like a fingerprint for the target material. The peaks also depend on the applied voltage across the tube. This is important because electrons in atoms are distributed in energy shells with different binding energies. Electron binding energies are characteristic of the type of element. A characteristic X-ray is produced when the electron kinetic energy exceeds the binding energy of an electron in an atomic shell. When the electron is removed from, say, a K shell, an electron from an adjacent shell, say the L shell, will fall into the K shell and in the process emit a characteristic X-ray with energy equal to the difference in binding energy between the shells. On this slide, we have a table of the binding energies of various target materials. Tungsten is the material most used for X-ray imaging. Molybdenum and rhodium are used for mammography imaging, with molybdenum being the most common. With digital detectors, tungsten is also becoming the target of choice in mammography. We will talk more about this when we get to the lecture on mammography. For characteristic X-ray production, it is important that the electron kinetic energy be greater than the binding energy of the electron shells. When this is the case, the electrons can be removed from the energy shells and characteristic X-rays can be produced by electron transitions between a filled shell and a vacant shell. This table shows characteristic X-ray energies of a few target materials. The tungsten K-alpha characteristic X-ray is the X-ray produced by a transition between the L electron shell and the K shell. If the label is K-beta, then the transition is between the M shell electron and the K shell vacancy. The bottom left figure shows the transitions of a tungsten element. Although most of the kinetic energy of electrons produce heat in the anode, of the small proportion that produce X-rays, 5% of that is characteristic X-rays. These transitions shown in the bottom left figure lead to characteristic X-ray production. The ejected electron can eject other electrons from lower energy levels. These electrons are called Auger or transfer electrons. This is shown in the top right figure. The top figure shows a characteristic X-ray spectrum with various X-ray spikes due to transitions to the K, L, and M shells. The higher energies are the K shell X-rays and the lower energies are L and M shell X-rays. The bottom slide shows a filtered Bremsstrahlung X-ray spectrum with the K characteristic spikes showing above it. M and L characteristic X-rays are not shown. The influence of tube potential on the Bremsstrahlung X-ray spectrum is shown here. At higher tube potentials, the effective energy is shifted slightly higher and the maximal energy is also increased. The intensity of radiation also increases with the tube potential increase. Note that the characteristic X-rays are unchanged in position except for an increase in intensity. The influence of tube current is shown on this slide. The tube potential is 100 kV and the exposure time is the same for all three spectra. Note the position of the maximal energy. It is near 100 kV. The effect of tube current is to increase the quantity or intensity of X-rays. The tube potential is unchanged, so the effective energy as well as the maximal X-ray energy are unchanged with changing tube current. Note the position of the characteristic X-rays. Again, their position is unchanged, but their intensity is increased with increased tube current. The effect of filtration is shown on this slide. Remember that filtration hardens the beam. On this slide, adding filtration does not change the maximal X-ray energy, but rather shifts the peak energy to higher energies. The intensity of X-rays is reduced with added filtration. Note the position of the characteristic X-rays as the filtration is changed. The only change in characteristic X-ray is in intensity. Beam hardening is the removal of low-energy X-rays from the beam by the process of photoelectric absorption. Beam hardening is done by adding filtration to the beam. The filter preferentially absorbs the low-energy photons. Removing low energy photons is important because low energy photons increase patient dose but do not contribute to image quality. Removing low energy photons increases the quality of the X-ray beam. Increased beam quality is characterized by increased half-value layer. A harder beam is useful because it can penetrate denser or harder materials. Also, beam hardening reduces the intensity of the beam. Another way to reduce X-ray intensity is to increase distance from the photon source. The principle involved is the inverse square law. It works because as the distance increases, the area of the region the X-rays pass through increases in a squared fashion. An intuitive way to think about it is as follows. If you double distance from the source, the intensity is decreased by a factor of 4, and if you triple distance from the source, intensity is decreased by a factor of 9. If distance is quadrupled, intensity is decreased by a factor of 16 and so on. You can also go the other way with this exercise. If the distance from the source is cut in half, the intensity is increased by a factor of 4, and if the distance is cut by a third, the intensity is increased by a factor of 9 and so on. This figure shows a simple example of how to calculate intensity at area 2 using the inverse square law. Modern X-ray systems all have one essential component in common, the X-ray tube. Here is a picture of an early radiographic system. This system used a type of tube called a stationary X-ray tube. We shall see that next. Here is a clearer picture of a stationary X-ray tube housing shown on the previous slide. The cathode and anode insets are also shown. When you look closely at the stationary X-ray tube, you see the filament embedded in the cathode. The anode is made of the target material embedded in a copper block. The copper block serves a useful purpose. It conducts both heat and electricity and also acts as a mechanical support for the target material. X-ray tubes are placed in a protective housing. On this slide, we can see the tube housing with the locations of the high voltage cables for anode and cathode connections. The collimator is also shown in the bottom image. By looking at the cables, we can know the location of the cathode and anode. The anode cable is positive and the cathode cable is negative. Here is a cutout figure of the X-ray tube housing showing the insides. This is a typical arrangement for a modern X-ray tube. One important difference between this tube and the stationary X-ray tube is the rotating anode. This cutout shows the X-ray tube insert, which is a high vacuum glass envelope containing the anode and cathode. There is an output port for X-rays to exit. There are also high voltage cable sockets and an anode rotor and stator windings. Let's look at the cathode component first. The cathode is the negative electrode in the X-ray tube. It consists of a filament and a focusing cap. The filament is made of thoriated tungsten wire wound in a helix. Thoriated means it is doped with thorium. The filament is the part that produces the electrons by the process of thermionic emission. A small current on the order of 1 to 5 amperes is applied to the filament by a potential drop of about 10 volts. At this current and voltage, the filament heats up and emits electrons by thermionic emission. The electrons are accelerated across the tube by applying a large potential difference between the anode and cathode. Tungsten is the target material of choice because it has a high melting point of 3410 degrees Celsius. It also has a high atomic number Z, which results in high X-ray production efficiency. Most X-ray tubes for diagnostic imaging have two filaments of different lengths. Each filament can be selected depending on the imaging task at hand. The focusing cap is an important part of the cathode. It shapes the electron beam so it can be focused onto the anode target. The focusing cap can be maintained at the same potential as the filament. This allows electrons produced by the filament to be shaped by the cap before accelerating across the tube. Both focusing cap and filament are maintained at a negative potential relative to the anode. In the top picture, we see the focusing cap with two filaments. The bottom figure shows a bit more clearly the two filaments in a focusing cap. The importance of the focusing cap is shown in these figures. Focusing is done by applying a bias voltage to the cap. As electrons flow from the cathode to the anode, the electron beam is spread out if there is no focusing. This is shown in the top part of the left figure. The bottom part of the left figure shows the effect of the focusing cap on narrowing the electron beam. Clearer effects are shown in the figure on the right for both the unbiased and biased focusing cap. The flow of electrons from the focusing cap to the anode is called the tube current. Tube currents range from 10 milliamps to 1100 milliamps and can be selected depending on the task at hand. For example, when a technology selects a technique on an X-ray tube, they may select, say, 80 kV and 500 mA. 80 kV is the potential difference between the cathode and anode in the X-ray tube. 500 mA is the tube current of electrons between the cathode and anode. An X-ray tube having two filaments is called a dual focus tube. Having two filaments allows different focal spots to be selected for imaging. The size of the filament relates to the size of the focal spot. The focal spot size determines partly the spatial resolution as well as the amount of tube current available for imaging. The large filament will produce more electrons when heated compared to the small filament, so the tube current is higher for the large filament compared to the small filament. When large anatomies are to be imaged, the large filament is selected. When fine structure and small anatomies are to be imaged, the small filament is selected. Here are some pictures of X-ray tube insets. A cutout is also shown with the parts labeled on the top left figure. Here is a summary of what we've learned so far. We started off with Bremsstrahlung X-ray production and looked at how X-rays are produced by electron interaction with the target nucleus. The Bremsstrahlung spectrum is called a continuous spectrum. We also looked at the production of discrete X-rays from the transition of electrons between energy shells and atoms of the target. We mentioned that the discrete spectrum is unique to an element and is a fingerprint for that element. The discrete spectrum is possible when tube electrons have enough energy to overcome the binding energy of the electrons in the energy shells. The difference in binding energy between the shells involved in a transition is the energy of the characteristic X-ray. We looked at the filtered and unfiltered spectrum and the consequences of filtration in terms of beam hardening, reduction in intensity, and increase in peak energy. I also discussed the importance of filtration in increasing beam quality and reducing patient dose. Now let's look at a few questions to finish up. Let's finish up with a few questions. First question, which of these is not an X-ray target used in mammography? Your choices are tungsten, lead, molybdenum, rhodium. The correct choice is lead. Next question. The maximal X-ray photon energy produced by an X-ray tube is determined by, and your choices are tube potential, filtration, tube current, target material. The correct choice is tube potential. Next question. The magnitude or intensity of X-ray photons is affected more by, and your choices are 0 mm aluminum, 0.5 mm aluminum, 3 mm aluminum, 1.5 mm aluminum. The correct choice is 3 mm of aluminum. These are short answer questions. The first question, how does adding filtration to the X-ray beam affect the quantity of X-rays reaching the image receptor? The correct answer is filtration reduces the intensity or quantity of X-rays reaching the target. The next question, how does filtration affect the quality of the beam? The correct answer is filtration increases the quality of the X-ray beam. Next question, why are X-ray tubes manufactured with two focal spots? Having two focal spots allows the technologist a choice between a small focal spot that is limited in X-ray output but allows higher spatial resolution imaging, and a large focal spot that allows imaging of thicker anatomy where more X-ray photons are needed to reduce noise. This is the last slide of the presentation. Thank you for watching.